Every single time you click or type or connect to anything, you're leaving behind a story. Most of the time, that story just fades away. But sometimes, that story needs to be brought back, piece by tiny piece from the digital silence. Welcome to the incredible world of digital forensics. And that right there is the fundamental challenge. The evidence isn't a fingerprint on a glass. It's more like a ghost in the machine, a whisper in the wiring. And the absolute first job of any investigator is to capture that whisper without changing it in any way, shape, or form. So how do they do it? How do you possibly handle something you can't even see and make sure it holds up in a court of law? Well, it all comes down to a super strict, methodical process where just one wrong move could cause the entire case to just fall apart. You gotta understand, this isn't guesswork. Every single digital investigation follows this exact methodology. It ensures the evidence is sound and admissible. Now, after preparing for and seizing the device, the next step is maybe the most critical of all: preservation. You have to create a perfect copy. Okay, so here's the #1 rule. You never, ever work on the original evidence. Ever. Instead, you create what's called a forensic image, a perfect copy. And as you can see, they come in two main flavors. A logical image just kind of grabs the files you can see, like what's on your C drive. But the physical image, that's the gold standard. It is an exact bit-for-bit clone of the entire drive. We're talking deleted files, hidden partitions, all that so-called empty space, the whole shebang. So how do they pull that off without changing the original? They use this little gadget. It's a hardware write blocker. Think of it as a one-way street for data. Information can flow from the original drive to make the copy, but absolutely nothing can be written back to it. It physically guarantees that the original evidence stays completely pristine and untouched. Okay, so you've made a copy, but how do you prove it's a perfect identical twin? The answer is something called hashing. You run both the original drive and your new copy through a special algorithm, like MD5 or SHA-1. What comes out is a unique digital fingerprint, a long string of characters. If those two fingerprints match, character for character, boom, you have mathematical proof that your copy is perfect. If they don't, even by 1 bit, that evidence is considered contaminated. It's that precise. So we've got our perfect mathematically verified copy. Now, the real magic begins. Now, we start looking for the things that someone tried to make disappear. We're going hunting for the ghosts in the machine.
Come on, we've all done this, right? You drag a file to the recycle bin, you hit empty, and you just assume, poof, it's gone forever. But is it really?
Let's just pause and really think about that for a second. When you tell your computer to delete something, what is it actually doing under the hood? The answer, at least for most systems like Windows, is a resounding no. Deleting a file doesn't actually wipe the data. It just removes the pointer to that data. The analogy here is perfect. It's like going to an old library card catalog and just pulling out the card for a book. The book itself? It's still sitting right there on the shelf, completely intact, just waiting for a new book to take its place. Your data is still there, in what's now called unallocated space. So, if there's no card in the catalog, how in the world do you find the book? Well, you use a brilliant technique called file carving. This is where special tools just ignore the file system and scan through all of that empty, unallocated space, sector by sector, looking for the telltale signs of a file's beginning and end. And here's the secret sauce for how that works. Pretty much every file type has a unique header, a kind of digital signature. A JPEG image, for example, starts with the letters JFIF. A PDF document starts with %PDF. File carving software is designed to scour the drive for these digital breadcrumbs, and when it finds one, it knows a file used to be there and can start to piece it back together. Finding a deleted file is huge, don't get me wrong, but the real story, the full picture, is in the timeline. It's not just about what happened, but when it happened, and in what exact order. And the key to building that timeline is that every single file has its own hidden logbook. In Windows, this metadata, this logbook, stores at least 4 crucial timestamps: when the file was first created, when it was last modified or saved, when it was last opened or accessed, and even when its entry in the master file table was changed. Okay, now this is where it gets really clever. These timestamps change in predictable ways depending on what the user does. Take a close look here. When you copy a file, the brand new copy gets a fresh creation time. But if you simply move a file on the same drive, the original creation time stays the same. That tiny little detail allows an investigator to tell the difference between someone making a copy of a sensitive document versus someone who is just reorganizing their folders. It's incredible.
And when you start putting all these timestamp clues together from hundreds, maybe thousands of files, you can rebuild the story, moment by moment. You can see the sequence of events unfold. Here's the malicious PDF being downloaded. There's the moment it was opened. The exact time-sensitive data was copied. And finally, the attempt to cover their tracks by deleting the evidence.
So we've recovered files from the void, and we've built a timeline. But what about physical interactions? What about tracing a user's actual digital footprints? Let's start with something as simple as plugging in a USB drive. Believe it or not, even if a USB drive was plugged in for just a few seconds, it leaves a permanent record. Think of the Windows registry as the computer's giant central database of everything. Well, within it, there's a specific key called USB Store that acts like a guestbook. It meticulously records the brand, the model, and, most importantly, the unique serial number of every single storage device that has ever been plugged in. Okay, so knowing what was plugged in is fantastic, but knowing when is even better. Another digital breadcrumb, this time in a system log file, records the exact moment the operating system first saw and installed that device. So now we've got the make, the model, the unique serial number, and the precise time it first made contact with that machine.
But here's the kicker. What if the suspect got rid of the USB drive? How can you possibly know what was on it? Well, often the answer lies in these little things called link files. You know them as shortcuts. Windows creates them automatically when you open files, especially from external drives. And that little shortcut file can contain a goldmine of information: the original file path, timestamps, and even the serial number of the USB drive it came from, proving what files were on a drive long after it's gone.
Now, everything we've talked about so far is called dead box forensics, analyzing a machine that's turned off. But what if the attack is happening right now? That calls for a totally different, much more urgent approach: live memory analysis.
See, a computer's RAM is like its short-term memory. It's incredibly volatile. It's constantly changing, constantly being overwritten. The moment you pull the plug, everything in it vanishes forever. This means capturing a snapshot of that live memory is a frantic race against the clock, because every single second that passes could mean crucial evidence is lost for good.
So why go to all that trouble? Because RAM contains the evidence of what's happening right now. It holds all the running programs, the active network connections to a hacker's server, sometimes even passwords and encryption keys in plain text, and commands that a user just typed. This is the kind of stuff that may never get written down to the hard drive. And this right here really shows you the power of digging into that live memory. The command on the left, pslist, it just gives you a flat, kind of boring list of all the programs that are running. But the one on the right, pstree, turns that list into a family tree. You can see exactly which program launched another one. This is how investigators spot malware that's trying to hide inside a legitimate program, like your web browser. They can trace it right back to its suspicious parent. So, from deleted files and hidden timelines to the ghost of a USB drive and the fleeting secrets in live memory, what digital forensics really shows us is that almost nothing is ever truly gone. It's just waiting to be found. It leaves you wondering, doesn't it? What stories are your devices quietly holding on to right now?